Hi guys, we're going to be going over a couple of the standards in the upcoming videos. These are for review, and this is kind of a specific standard that we're going to be looking at today. It is 8.ESS2. This is Earth's systems, and this is the fourth standard, which we're going to be going over a little bit today. And let's just look at that together for a moment. On this, you're going to gather and evaluate evidence that energy from the Earth's interior drives convection cycles within the asthenosphere, which creates changes within the lithosphere, including plate movements, plate boundaries, and seafloor spreading. In order to go over these, we are going to discuss a little bit about the lithosphere and the asthenosphere. We're going to talk a little bit about plate movements and seafloor spreading. This is going to be pretty much of a review, and how the convection cycles drive these. Okay, let's look, I talked a little bit about looking at the lithosphere and the asthenosphere. As I talked earlier, when we were in fourth grade, you learned that the Earth was divided into three main parts: the crust, the mantle, and the core. But as we have gotten older, we understand that there can be more specifics drawn from that. For example, the core is now divided into the outer core and the inner core, and the mantle and crust have been divided up into the lithosphere, asthenosphere, and mesosphere. So as we look at those, we understand that the lithosphere section's bigger than the crust alone. And so if we look at it, excuse me, just one second. As you look at it, you understand that the crust also is added to a little bit of this upper part of the mantle to create the lithosphere. And then the asthenosphere is the layer just below it, where it's just a little bit more fluid. In other words, the convection cycles can work at that point. And so next we're going to look at those convection cycles. Okay, convection currents are basically where heat rises, and this happens in the atmosphere, it happens in the oceans, and it also happens down under the crust, down in the asthenosphere, where the rock is a little more molten and it has a little more fluidity to it. But if we always remember that hot air rises, hot things rise, then the opposite of that is that cold sinks. And so with that happening, it creates a cycle. So as things are warmed up, they begin to rise, they cool off, they begin to sink. And so that creates a cycle, a type of kind of a little circle and a flow that we use to determine why plates move. And that's called plate tectonics. And so I'm going to watch a little video with you here in just a second about how the hot air or the hot liquid or the hot molten rock will rise, and then the colder things will become more dense, and then they will sink. Okay, we're going to click this link and we're going to watch this. Okay, I would like to stop right there and just to kind of give you, you have the visual, and I know it's kind of been a little bit spotty, but if you notice that the red is where he had the food coloring, and this is something you can actually try at home, but they had a copy of a cup of warm water in the middle, and then they had cooler water on the sides to support the tank. This was obviously in a liquid where we could see it, but as it heated, the food coloring went up. And if you notice, it's going off in two directions. Some is going off to the right, some is going off to the left. As it moves away from the heat source, it gets cooler and then you notice it sinks, and there is no void left in there. It is replaced by the cooler, denser material. Now, you can visualize this in an ocean or in water, but you can also visualize this in air. Think of this as wind. A lot of times we have weather where we have warm air rising and then the cold air coming in below it. And obviously, if there's an extreme temperature change, then those winds are going to be a lot stronger. I know I think about in weather when it's been very, very windy, then I know there's probably going to be a temperature change coming in some form. And so this happens, and we see it with wind, we see it with ocean currents, but this also happens down within the more fluid parts of the earth where it's not quite as solid. The deeper you go in the earth, we know that the pressure and the temperature increase, and so um, that hotter material is going to become less dense, it's going to rise, and then the cooler air will take its place. Okay, once again, this is the link that you can click on uh, to get to the full video, but I wanted you to get a sense of what convection currents were. We can visualize those in the liquid forms with food coloring much better than we could in the atmosphere, and certainly under the earth. We would never be able to really see that. Illustration of how those convection currents may work. This is a little picture. It shows the plates. This is the green parts. This is the lithosphere. And you see down in the mantle and in the asthenosphere, you have those convection currents working. And as they go around and around, some goes off to the right, some goes off to the left, and this pulls plates apart. And this ends up being seafloor spreading. And this is a boundary called a divergent boundary. It's where they are going apart. And that is our seafloor spreading, and those are caused by convection currents. With the convection currents moving in opposite directions, which pull the plate apart, this allows the magma to come up through the middle, and when it does, it cools because it's an oceanic plate. There's water above it. That water is going to cool it, but it doesn't cool it immediately. And so it kind of gets out of there a little bit and then it cools. And as you can tell, then it's going to create a ridge, which is going to create like a mountain chain under the earth, under the oceans. And this is where the seafloor is spreading. New crust is being created right here. And then on this other end, uh, it's going to move under a continental plate, which is drier. It's going to be less dense than the oceanic plate. The oceanic plate is going to be pulled down due to gravity, and that's where we have our divergent boundary. Okay, I hope that this has helped you to some degree to understand that the lithosphere is a part, it has the um, crust and the uppermost part of the mantle. Below that is the asthenosphere. The mesosphere is below that, but these convection currents work together to move the plates apart in what we call plate tectonics. As they move apart, it is a divergent boundary, and this is where there is seafloor spreading, and this is where the mid-ocean ridge comes into play. And so hopefully that has helped you if you had any confusion about this standard, and I will see you on a following video. Thank you.